All right. Hello, everyone. Thanks for joining us for our next talk here. Super excited to introduce Yi Sun, founder of Axiom, who's going to be talking to us about OpenVM. So give it up for Yi.
Awesome. Yeah, so my name's Yi. I'm excited to tell you guys a little bit about OpenVM, which is a modular and performant zkVM framework. So first, just for some background, the purpose of OpenVM is to allow developers to generate zero-knowledge proofs. And so I thought I'd begin with a summary of what zk allows you to do. So the premise of zk is that you have a prover, we're calling Alice here, who has a computer program. And what zk allows Alice to do is to make a claim about what the output of that program is on some input. And then there's a verifier named Bob who's skeptical about the claim. So Bob doesn't trust Alice, and Bob will ask Alice to provide some cryptographic data, which is called a proof. And the point of zk is that using the proof alone, Bob can verify that Alice actually correctly evaluated the program and gave him the correct output for the program. And one special property of zk is that this can actually work for arbitrary computer programs. Now, to make that real, recently a new concept called a zk virtual machine has been developed. And so this is to solve the problem that it's actually very difficult traditionally to use zk. So traditionally how zk worked is that a prover would start with a computer program, and then to zk verify execution of that program, they would need to translate the program into something called a zk circuit. So a zk circuit is a system of polynomial equations such that knowing a solution to that system is equivalent to knowing an execution trace of the original program. Here I tried to show it with a quadratic polynomial, but in practice these polynomial systems are extremely complicated and very challenging for developers to actually write. So the premise of a zkVM is to allow developers to directly generate zero-knowledge proofs for programs written in normal programming languages like Rust. And the way that they do that is by splitting the workload of generating a zero-knowledge proof into two pieces. First, a zkVM is a very special circuit that's hyper-optimized to verify an interpreter for a virtual machine or an ISA. And then when a developer writes a computer program in that virtual machine, then the zk circuit of the zkVM is able to verify that that program was correctly interpreted and gives the correct output. And so that would imply that the program actually executes to the claimed output. What this means for developers is that they don't need to know any details about zk to generate zero-knowledge proofs for their programs. All they have to do is write in a supported programming language, which is then compiled to a binary that's actually run against the zkVM. So there are a bunch of existing approaches for zkVMs, beginning with the earliest ones, probably the earliest would be Cairo. And so in general, when considering a zk virtual machine, developers today have to trade off between performance and flexibility. The core choice they have to make is what sort of instruction set should be supported by the virtual machine. And they roughly have two classes of choices. The first is to pick something that's very zk specific. So Cairo and Velita support new ISAs that were invented specifically for the purpose of being convenient in zk. And so this has a lot of performance advantages, which is why the developers of those systems chose this. However, they have the significant downside that they're not really compatible with standard programming languages. And the developers of these systems have created new programming languages that developers must rewrite their programs in to use these zkVMs. And so obviously that's a pretty big developer experience bottleneck. The other option is for developers to use a more traditional ISA, something like RISC-V or WebAssembly, that's already used as a compilation target for normal programming languages. For example, RISC-V is used in open source processors, and WebAssembly is very commonly used in the browser. The big advantage of this is that it makes it possible for developers to use existing programs written in existing programming languages. For example, things like Rust or Go, or maybe Zig, as in the previous talk. But the problem with this is that there can be substantial performance overhead because the ZK system is not actually adapted to this existing instruction set architecture, which is optimized for physical hardware. And so existing zkVMs fundamentally require the developer to choose between performance and flexibility for this reason. And so the question that we came to while developing OpenVM was whether we can remove this trade-off and develop a ZK system that balances both. And so the answer we came to is to give developers a choice between them in a more fine-grained way by developing a more modular zkVM. And so I wanted to now tell you about the solution we've developed, which is called OpenVM. So it's a modular and performant zkVM, where the focus of the architecture is on customization and extensibility. And so there are 4 key features that I want to go through in this talk. The first is just what OpenVM does at the developer level in terms of allowing developers to prove the execution of arbitrary Rust programs. Then I'll talk about the modularity property, which allows developers to generate proofs for programs in arbitrary ISAs. And finally, talk a little bit about what happens behind the scenes to enable this. So first, what OpenVM offers for a developer is the ability to prove unbounded execution of just standard Rust programs. So the flow of generating a zero-knowledge proof using OpenVM has 3 steps. The first is that developer writes a Rust program encapsulating the execution they want to verify. And then they build it through a special OpenVM build process into a program binary that we are going to verify the execution of. Then using OpenVM, they can generate some relatively larger ZK proofs using a type of ZK proof system called a ZK Stark. And finally, those proofs can be recursed to make them amenable for verification on different blockchains. So currently, we support EVM verification, but in the future, we're probably going to add support for other blockchains as well. So through this process, if you start with just a standard Rust program you're interested in, perhaps something like the state transition function of a rollup, then you can use OpenVM to generate a zero-knowledge proof for your rollup state transition and settle it on Ethereum. OK, so that's kind of what OpenVM allows developers to do at a high level. But what if you're a more advanced developer and you want a little bit more? What we allow developers to do is to customize OpenVM through a concept of VM extensions. So what that means is we allow developers to define their own sets of opcodes and add support for them in OpenVM while ensuring that those opcodes are going to interoperate over common address spaces. So of course, we developed a set of default opcodes. So OpenVM ships with RISC-V, recursion, elliptic curve cryptography, and hashing support. But our architecture actually allows developers to create a new VM extension to accelerate performance in their specific use case. And these extensions could be very program-specific and perhaps not relevant for other users of OpenVM. Now, the design of OpenVM is actually extension first. So all functionality in the VM is implemented through these extensions, including RISC-V support and recursion support. And so as a consequence of this architecture, we actually allow developers to add their own extensions on equal footing with this default set of extensions. And one core feature we have is that developers can add extensions without forking or modifying the OpenVM core repo. All they need to do is import OpenVM as a library. OK, so now I want to talk a little bit about how the design of OpenVM actually enables this modularity. So one observation we had when looking at all existing zkVMs is that the design is actually a little bit skeuomorphic to how physical processors in your computer would work. Notably, in all existing zkVMs, there is a circuit which is called the CPU circuit. And the job of that CPU circuit is to verify that the execution of different opcodes is done correctly. So with OpenVM, we've introduced a new way to verify execution, which we're calling a no CPU architecture. And the core feature is that it does not have a CPU circuit. Instead, the execution consistency check is spread out between the circuits for all of the opcodes. And so what that means is that developers can freely add new opcodes by simply writing ZK constraints and circuits, backing the opcodes that they're interested in that satisfy certain input and output post and preconditions. And the overall no CPU architecture will make sure that the execution consistency involving those opcodes is constrained correctly. And so that's what enables us to allow developers to add VM extensions in their own repos without having to fork the upstream or modify the upstream. Finally, the pace of development in ZK is pretty fast these days. And obviously, one extremely important feature of any ZK system is the underlying ZK proof system. So one concern for any developer using a ZK VM or any other ZK infrastructure is just that maybe they choose the wrong proof system and their application is left behind. And so with OpenVM, our approach to this is to allow developers to incrementally experiment with new proof systems. Now, the way we enable that is to enable different parts of OpenVM to use different proof systems. In contrast to existing systems, where if you want to test out a new proof system, you pretty much have to rewrite a new zkVM from scratch, which takes many months of developer time and is not super practical. So in our model, we're able to take individual components, use a new and allegedly better proof system to prove them, and then benchmark the difference between that and the previous proof system that's used by default. And so that allows us to incrementally experiment with new proof systems and just incrementally upgrade OpenVM to use them. And ultimately, what we want to deliver for developers is a future-proof experience for any new developments in ZK. Research is happening very quickly, and we believe what developers want is a single platform that can continuously keep up with the latest state of the art. All right, so just to give a sense of where we are, we first announced OpenVM in December, right before the holidays. And we evaluate our performance on the time it takes to verify the execution of a single Ethereum mainnet block using the RETH node. And so today, we're using CPU benchmarks. We're able to prove a mainnet block in about 9 minutes on a single machine, or a little under 3 minutes using multiple machines. And as you can see, the progression since our release in December has been pretty rapid. In December, the single machine proving time was over 40 minutes, and the multi-machine proving time was around 20 minutes. So we've come down about 5 to 6x on both numbers since then. In the coming months, we're going to introduce GPU acceleration, and we expect some pretty significant decreases from these numbers from that. Lastly, we want to build an open development ecosystem for OpenVM. So I'm one of the founders of Axiom, but we built OpenVM in collaboration with contributors from Scroll, as well as some independent ZK researchers, such as Max Gillett. And we actually believe that the ultimate zkVM framework that's most robust for developers will have multiple contributing teams that are each using the VM for their own product purposes. So yeah, we're really excited to grow the contributor community in the coming months. So if you'd like to learn more about OpenVM, put a bunch of links on the slide. We have a very technical developer chat. And if you'd like support in implementing or using OpenVM for your infrastructure or application, we have an interest form for Axiom at the bottom of the slide. That's it.